Hello guys, one quick example of influence lines, but this time with girders that have floor beams on top of them, and how the load is distributed from those floor beams to the girders. These type of cases usually you can see them in bridges and some type of buildings also, but mainly in bridges. So let's work this example out, and I'm gonna explain you what is happening here. So basically, when you have a regular beam, a regular girder, and you don't have these floor beams, you can do the influence lines at any point that you want to. Now when you have these panels here, these panels and these floor beams, you can put the load anywhere that you want to on top of the panels, but effectively it's like the best location for the load is on top of the floor beams, because those are the ones that are going to be transmitting the load to the girder, and the shear within the panel is going to be constant because it's the same due to that load. So let's see how do you this is too much words, and the analysis is extremely similar to the regular analysis that we do. So the first thing is recognizing, I'm missing this point F here, recognizing that we have to calculate these reactions AY and FY, and we are going to be moving the load as we always do, and the first location of the load is going to be here on top of that point A, or that support A. So we are going to do first load at the support A. If the load is at the support A, I can do all the analysis that you want to, but at this level you don't have to do anything. I mean, just look at that load. The load is, what is that? Alarm? Hope not. It always catches me when I'm writing a video. Okay, I don't know if I'm gonna get killed here. Let's see. So, nice. I understood everything perfectly. Okay, anyway, you have that load. Hash! You have that load over there of 1, and that load is acting on top of the support AY. None of that load is going to be applied in the girder itself, because it's absorbed completely by the support A. Meaning, whatever I'm calculating here is going to be 0. So the shear at the panel BC is 0, and the moment at D, which is the other question that this problem is asking, is also going to be 0. So second. Now let's move the load, and the load, it was here, and now we are going to put the load there. So the load is not there anymore, and the load is in the location B. If I do that, so let's do it. It's the same thing that we did before. You just calculate the reactions first. Summation of moments at F equals 0. Why at F? Because I want to calculate AY, I'm working with this side of the beam. So if I do moment at F, summation of moments at F for the global reactions equals 0. I'm going to have AY multiplied by 10 negative plus 1 multiplied by 8. 8 times 1, meaning AY is going to be 0.8. There you go. Reaction 0.8. Now once we have the reaction, we can come and we just do this little cut. Remember, I'm interested in the shear at B, which is going to be the same across the panel. So I'm going to do that. If I do that, then I'm going to have this AY 0.8. I'm going to have this distance, which is 2. This is A, this is B. My load is here and this instant at B, and I'm going to have a shear at B. By doing summation of forces in Y equals 0, then you can get that the 0.8 minus 1 minus BB equals 0, or BB, which is not BB, actually it's BBC, but I call it just BB, equals negative 0.2. Now, if we are working with the moment. Forget about this part. We're working with the moment. We do exactly the same thing. This is gonna be the point D, and the load is placed here at the point B. My reaction AY is 0.8. This distance here is 2, and this is 2 plus 2, 4. And if I do, well, and then I'm going to have the moment here. Of course I have a moment here. I'm not interested in that, in the same way that I'm not interested in this, because I'm not calculating shear for this portion. So the moment at D, if I do summation of moments at D equals 0, then you get 0.8 negative 0.8 times 6 plus 1 times 4 equal 0, and this is a 4.8 minus 4, 0.8, so MD equals 0.8. There you go. Moving the load. Moving the load. Move the load. Now I just move the load, and the only thing that I came to my mind is follow the leader. Okay, move the load over there. Now this is interesting what is happening here. So we are gonna say load at C. Oh, look at that, I forgot to put here load at B. Okay, now the load is at C. If the load is at C, look what is happening. My beam is here. This is A, this is B, and the load is here at C, right there. So if that is the situation, and this is I can calculate the reaction, of course, but I'm going to show you a shortcut for that. But what I'm trying to tell you is, when I calculate my shear here, the load is not on top of this portion, so this one is not affecting it. It's not affecting it directly, it's just affecting it in the global reactions for AY, which I didn't calculate. Now, I don't know if you realize the pattern that is here, but there is a pattern when you have this type of moving loads. And that's going to help you also when you are taking the FE or the PE later on, that you have to do calculations really quick. If you have these type of situations and you have one concentrated load, the load at this point for this simple supported beam, the load at this reaction is just going to be bigger or smaller. This load, if the load is in that position or closer to this support, has to be bigger than the load at the other support. So what you do is that you say, oh, this load multiplied by this distance divided by the total is going to be the value here. Let's see how that works. If whatever I predicted is correct, the reaction in Y should be, when the load is at C, should be 6 times the load divided by the total distance, 10. And this is 0.6. Let's just calculate regularly summation of moment at F equals 0 to see what happened. If I do moment at F, that's what is happening, right? Negative AY times 10. So it's going to be negative AY times 10 plus 6 times 1 equals 0. So AY equals that. So you don't have to calculate it every single time. Usually when we do trusses also, that helps you a lot with the calculation. So now you know this value here is 0.6. And if you do summation of forces in Y, you can calculate that BB is equal to 0.6. Done. Now what about the moment? Well, let's try what happened with the moment. I have my reaction of 0.6. The load is at C, right there, C. This distance from here to here is 4, and we are interested in the point D, right there, and this distance is 2, and this is the moment, internal moment at D. So if we do that and we do summation of moments at D equals 0 to calculate that value, then you're going to have what? You're going to have a 0.6, 0.6, where am I? Load is at C, and I'm calculating the moment here, right? 0.6 times 6, 0.6 times 6 negative times 6 plus 1 times 2 plus MD equals 0, and this is what, 3.6 negative plus 2 positive, negative 1.6, pass it to the other side, 1.6. Got it. Okay, now fourth, when the load is at D, the load is at D, follow the leader, there you go, there, not the liter, the liter is the garbage, follow the leader, there, 1. So if I do that, you do again summation of forces, summation of moments at F equals 0 globally, just to calculate reactions. But if you were paying attention to whatever I was telling you, the reaction at this point, because this distance is bigger than this distance, is going to be this one, 4 divided by 10. So AY is equal to 0.4. And if I do the analysis, what I'm going to have is basically the same drawing that I have here. The load is somewhere here, and I don't care about that anymore. Load applied at D. But this point here is A, and this point here is B, and this is my shear, calculating it. And this value is 0.4, meaning the shear also, when you do summation of forces in Y, is going to be 0.4, and you have this value correct there. Now, when doing the moment, let's see what happened. Now, the load is at D, and I want to calculate the moment at D. So this is the point D. The load is at D, right there. The reaction here is 0.4, and this distance from here to here is 246. When we do summation of moments at D for calculating the internal moment, it comes that 0.4 times 6 negative, the load doesn't produce any moment at that point, plus MD equals 0, meaning MD is going to be equal to 2.4. Now we move it, we're going to move the load from here, and we're going to put the load there. So the load is at E. Load at E. When the load is at E, if the load is here, this reaction is going to be 2 divided by 10, 0.2. And you do the same analysis, and you say, okay, I'm gonna do it because it's the first example, but you don't have to do it every single time. This is 0.2, the load is here, and this is the point E, and this is 0.2, so when I calculate this V, it's gonna be 0.2 by doing summation of forces in Y. Then you get that 0.2. And the moment, if you come here for the moment, then the situation is also similar to whatever we do before, but however, now this is happening. This is the point A with a reaction of 0.2. This is the point D, where the moment has to be calculated. The distance from here to here is 6 meters. This is my moment that I have to calculate, but the load is here at E. So that load is not going into this equation also because it's not on top of that part. So when you do summation of moments at D equals 0, then you get negative 0.2 times 6 plus MD equals 0, which gives you MD equals 1.2. And last but not least, that's a good title for a song. When the load is at F, right there, load is at F. So the load is going to move from here and it's going to be right there. What happens here? 5, 4, 3, 2, 1. Tell me. Exactly. Same thing that I explained you before at A. All the force is going to be absorbed by the support F absorbs the force, the external force, meaning AY is 0 and FY is 1, VB is 0 and MD is also 0, because now the load is not on top of the girder or on top of the panels. It's just directly on top of the support column, pier, wherever you want to call that support. Now, once we have all of these values, we just proceed to summarize that and plot that. Plot is the last step. What do? We put here this, we put here that. This is gonna be X in meters. This is gonna be the shear on the panel BC. And then we're gonna put this here, same thing. This is X in meters. And this is going to be the moment at D. The maximum is 10, so it's gonna be 2, 4, 6, 8, 10. 2, 4, 6, 8, 10 meters, of course. 8, 10. 2, 4, 6, 8, 10. And now we start plotting the values. And we say, okay, for 0 is 0. For what is the maximum here? The maximum here is at D, 2.4. Or you can put also letter C if you want to, but the letter D is at 6, so it's going to be here. But I was reading this one. So this is negative 0.2, negative 0.2, 0.6, 0.6, 0.6, negative 0.2, 0.6. When the load is A, B, oh no, that's not it, yes it is, no it's not, yes it is, no it's not, yes it is. This is 0, correct, and at 2 this is 0.2 negative, which is correct, and at 4 is 0.6, and then I have 0.4 when it's at D, 0.4, and 0. Where is the other part that we just did? Where are you? Who is taking my paper? Oh, it's here. 0.2 and 0. So it's going to be 0.2 and 0. And basically what you have is the influence line for the shear should be something like this, something like that, and like that. If this is a straight line. Do what I say, don't do what I do. That's a straight line. These two lines, by the way, should be parallel to each other, and I explain that later on in another problem. Now the moment, well, you should put the values, right? 0.4, 0.2, 0, and the moment is starts from 0 when the load is at A, and then 0.8, 1.6, 2.4, and the maximum is going to be here at 2.4, and then it comes to, where are you? Oh, here. Why are you hiding from me? 1.2 and 0 again. So this is easier because, you know, it's something like this and something like that. and now I can plot the values that they were like that if it was a scale. So this is 1.2, 1.2, 0, and this is 0, and this is 0.8, and this is 1.6. There you go. This is your first example of floor beams or calculation of influence lines for floor beams. What is the difference? Really? Not too much difference in the whole process of solving this. However, the students, I don't know why, most of the time they go crazy with this type of problems. Remember, what we're doing now is just drawing the influence lines. Now I'm going to go later on in the next part, and I'm going to explain how do you use this in order to design. See you next time, guys. Keep watching, keep learning, subscribe in case that you haven't, and see you around or not.